Good afternoon. Any questions before we start? All right. Today I'm gonna cover stress concentration factor. Then we are gonna talk about the curve mean. So far we just talked about straight mean. What if we have something like this, a crane hook, and we apply some force and moment, what's gonna be the stress due to the bending moment. So let's start with the stress concentration factor. Suppose we have a bar with the thickness of T, and this length is W. It's under axial load of F. So this bar, in the dimension, in the given dimension, this length is L, for example. If I ask you what would be the stress at any cross section, we can just cut this bar at that specific cross section and draw the free body diagram. Two forces apply to cross section. One goes up, the other one at the other end it goes down. So the sigma would be force divided by the area, which is W times T. The force is applied to this cross section. And now we don't have any discontinuity on this cross section. Now I'm gonna add a hole at the middle with the diameter of D. Just consider a hole at the middle of this bar. We would like to find the nominal stress, I label it as sigma O, on this bar. At which cross section I'm going to have the greatest normal stress. We can say that at this cross section, which has the less material, because we remove this hole, we are going to have the maximum normal stress. It's going to be equals to force divided by the area. Area would be W minus D times T. Instead of having W times T, we are going to remove this diameter because we don't have any material here. So the effective area is going to be W minus D times T.
Does W still mean the whole width of the...
Yes.
Okay,
Yep.
thanks.
Yep. I just remove the hole because we don't have any material. So now, we know that we have two types of the material, ductile material and brittle. We will talk about the details of these two types of the material later, but for now we know that we have two types of the material. So if this bar is made of ductile material, if someone asks you what would be the maximum stress applied to this bar, we can say it's going to be force divided by W minus D times T for ductile material. But if you have brittle material, for brittle material, if you do the experimental things, you will see that the sigma max is greater than the nominal stress that you calculated by this equation. So, and this is because the discontinuity that we have on the cross section, it makes the actual maximum stress greater than the nominal stress that we calculated from this equation. So then we define sigma max divided by sigma O as a K, which represents stress concentration factor. KT. KT is defined as the ratio of the maximum actual stress applied to the cross section, to this bar, divided by the nominal stress that is coming from the equation. So this is for the normal. If we are talking about the shear stress and the ratio of the maximum or actual maximum shear stress and nominal shear stress, then KT is gonna represented by KTS, which is shear stress concentration factor. So we have KT and KTS to represent the stress concentration factor. Is that so? In this slide, you will see this length is W. If I remove the material by putting this hole, the effective area would be W minus D times T, which is going to be a nominal stress, but the actual stress is going to be much greater than sigma O, and we define that as a stress concentration factor. It's applied for only brittle material. For ductile material, it's not going to be considered. Also, it's going to be applied, this stress concentration factor, when we have varying or dynamic loading. What do I mean by varying? Here, suppose F is 500 pounds. If I have constant value of the 500 pounds, then I have the static loading. But if I push 500 pounds and then release that, then again I push 500 pounds, then release that, F mean is going to be 0, no force. F max is going to be 500. So we are saying that we have varying loading or the dynamic loading because the load is varying over the time. So it makes another problem, which is fatigue. We will cover in chapter 6. But the stress concentration factor, no matter what type of the material we have on the component, should be considered on a varying load or dynamic loading. So either we have static loading with the brittle material or dynamic loading for both ductile or brittle material. We should consider this. So table A15 on the back of your book, it has the standard configuration of some standard configuration. Here we have something like this. If we have a rectangular cross section with a hole at the middle, which is under axial loading, what would be the KT? On this axis, you will calculate D over W. W is this thickness, and the D is the whole diameter. So you will find D over W, and then find the corresponding KT. So this is how you can find KT. Then you calculate the nominal stress multiplied by KT that you read from that graph, and you can find the maximum normal stress applied at this cross section passing through the hole. So this is how the concentration factor is 40. If I have a shaft with different diameter and the shaft is under bending moment, so it's under bending moment. The diameter of this, the bigger part is capital D, the lower side is lowercase d. It's under bending moment. We know that the maximum stress occurs in the smaller part because sigma is going to be 32 for the circular cross section, m divided by pi d power 3. M is going to be the same for both shaft. The smaller value for the D, we have the greater value for the normal stress. So we know that the critical section is going to be on the smaller side of the shaft. But due to discontinuity that I have in this shaft, because we have this cross section which has been shrunk to the smaller size, this curvature has a radius. So we call it as a R, or radius of curvature. You can measure, or you are given with that radius, you divide it by the smaller diameter, which is D, you read the number. So you know, suppose we are here, 0.2. Then, depending on the ratio between D and D, lower uppercase D and smaller diameter, you will find which curve you should move on. So suppose D over D is 3.2, goes up, 3 is going to be about 1 point, this is 1.6, this is 1.5. KT would be 1.5. So it means whatever number coming from this, sigma max is going to be 1.5 times sigma O. So the actual normal stress applied to this is going to happen at this cross section, and the magnitude is 1.5 times sigma O. If I had only the shaft with the smaller diameter, something like this, which was under bending moment, then sigma was MC, which is half of the diameter, divided by the I, which is the circular, pi d power 4 divided by 64. It's going to be 32m divided by pi d power 3. But this is for constant or continuous shaft. If we have discontinuity, then we should consider the stress concentration factor. As I said, it's going to be for, if we have static loading, it should be ignored for that kind of material. For the dynamic loading, for both type of the material should be considered. We will look at it at chapter 6 when we talk about fatigue. Good? So I just have two curves here, two graphs. If you look at table A15 at the back of the book, you will find 10 to 15 different standard configuration for different type of geometry or different type of the loading. So if it's talking about the normal stress, it's going to be KT. If it's talking about the shear stress, it's going to be KTS. Any question on this? All right. So now let's look at curved beam versus straight beam. We covered the straight beam. So we know that if one circular cross section is under bending moment, the normal stress is going to look like this. If this is x-axis, this is z-axis, and this is y-axis, the cross section is going to look like this: z-axis, y-axis. For straight beams, these are the things that we know about the straight beams: centroidal axis and neutral axis are coincident. So the location of the neutral axis, if this is the centroidal axis, the neutral axis is going to be at the same location. So they are the same. And two, stress. I will call these two sections as extreme fibers. Extreme fibers. Because they have the greatest distance at both sides of the neutral axis. So extreme fibers. Stress at extreme fibers are equal in magnitude and opposite in sign. So for this case of the loading, any point at the top of this line, the neutral axis is going to be under compression. So this line is going to get the maximum compressive stress, and this line is going to see the maximum tensile stress, but the magnitude would be the same for both extreme fibers because they have the same distance from the neutral axis. And three, linear variation in stress. Sigma is mz, for example, y divided by iz. So the normal stress is varying linearly with the distance, y distance from neutral axis, if it's under mz. So these are what we know about the straight beams. Here I define the curved beam. Suppose I have this curved beam which is under bending moment. I apply bending moment. So this curved beam, due to this curvature that I have, has a center of curvature. Suppose this point is center of curvature. If I have a straight beam, the center of curvature is going to be in infinity. But here I can imagine a center of curvature for the curved beam. So I can define Ri as an inner fiber radius. So the radius for the inner fiber. And I can have Ro as a radius for outer fiber. And if this is the centroidal axis, which is passing through the middle, centroidal section, the radius that I will call is RC, the radius of centroidal axis. It's passing through the middle of the beam. Now, if I compare these three for the curved beam, I can say that for curved beam, centroidal axis and neutral axis are not equal. So the neutral axis is going to be somewhere there, somewhere different. Suppose this is the location of neutral axis. I label with Rn. Rn, radius of neutral axis. So this Rn is different than Rc. So they are not equal. 2. Stress at extreme fibers are not equal to each other. So the stress here and stress in the inner fiber, they are not the same in magnitude. 3. We don't have linear variation in stress. We have hyperbolic variation in stress. So in a straight beam, it was varying linearly with the y, but here it's not varying linearly with the y. It's varying as a hyperbolic function over the beam. So let me define, suppose I would like to find the stress at this point. Point A. This is going to be R, the radius of that point. Rn minus R is defined as y, the distance from the neutral axis. So y Y is defined as a radial distance between Rn and R. So what is the R radius of neutral axis? What is the R radius of that specific point that we are looking for its stress? The other thing that I would like to define is E, eccentricity. Eccentricity is going to be defined the difference between RC and Rn. If you remember, we said that centroidal axis and neutral axis, they are not the same. So there is a difference between RC and Rn. Regular R is the radius of, we are looking for the stress. Yeah. R radius of the point. Any point that you want to find its normal stress.
Do we treat y and eccentricity as just a distance, so like always positive, or does their sign dictate the tension?
Y, I mean, Y below this line is going to be positive,
Okay.
and
so
the top of this line is
there's
going to
a
be
sign.
negative. So as you see, Y is Rn minus R. If R is greater than Rn, means it's going to be on the top of this line, we get negative value for the Y. If it's below this line, we are going to get positive because R is less than.
Thank you.
Yeah. So before we go through the equation,
Dr. Guppy,
yes, sir.
the eccentricity E, is that always positive? Because
Yes.
of, definition of, or
Mhm.
because of properties of the beam?
Yep.
Okay.
So
Just curious.
if we consider that as a distance, so I can put just absolute value. It's not always the case. Consider just a distance, not negative distance. All right. Here, MZ. MZ, if it was in the direction of positive M and Z direction, we consider as a positive. But the definition of the sign for the bending moment is different on the curved beam. If bending moment is positive if it tends to straighten the beam. Here, the way that I have the bending moment here, it tends to straighten the beam. So this bending moment should be considered as a positive. So if I have something like this, just in opposite direction, and I have the same direction for the moment, this bending moment is negative for this beam. This bending moment, I didn't change the direction of the beam and the direction of the moment. I just changed the curvature of the beam from that direction to that one. For this one, we should consider negative for the M. For this one, it should consider M as positive. So if it takes to straighten the beam, it should be positive, otherwise negative. So now I can I can introduce the equation which is going to give us normal stress. Normal stress can be obtained by m times y, whatever is the y for that point, divided by a cross section e Rn minus y. Where n is very important. Moment about centroidal. The value for the m is whatever is the moment about centroidal. Here you are given with the value of the m, so you know the value of the m. But if you have force times the distance to calculate m, this distance should be calculated from the centroidal section, not neutral axis. We will see one example about that. Y fiber distance from neutral axis, not centroidal. E is centricity. RC minus Rn. What else? A is the cross section. If I want to rewrite this equation in other form, AE Rn minus y, Rn minus y is going to give me R. So it's going to be AE times R, and y can be written as Rn minus R. So we will get the same result. I just remove. Here we have y, here we have R. Just different variable. Any questions so far? Now, let's do one. Doesn't like the timer. If this curvature beam is under positive bending moment, means the moment is applied in this direction because it tends to straighten the beam. What would be the stress in inner fiber? This side. Is it tensile or compression?
Tensile.
Tensile. So although it shows me kind of compressive, but it's before we apply the load. So the moment is gonna make the tensile stress, and here we are gonna have compression. So how can we find Rn? I should talk about the location of the neutral axis. The location of the neutral axis is coming by calculating this ratio. cross-section area, whatever is the cross-section, divided by the integration of dA over R. So I don't expect you to do the integration, just look at the table 3-4. For different cross-section, for rectangular, if I ask you what would be the RC, we want RC to find the eccentricity. It's going to be at the middle, which is Ri plus the half of the h. The Rn can be calculated by this equation. For this cross section, we have RC and Rn. For T shape, and for circular and other type of cross section, you can find RC and Rn. Stress at inner and outer surface. The only thing that you need to do is just plug in Y as a CI for the inner CI, and for the outer as a CO. MCI divided by ME times RI. Rn minus Y is R. It's Ri for the inner, and for outer it's going to be RO. Just if you want to have a summarized equation for stress at the inner and outer surface. And as you see, the stress is not varying linearly with Y. It's a hyperbolic function. It's varying, it's kind of hyperbolic function. So, any question before we start an example? All right. Suppose we have a hook for a crane. The outer diameter of this hook is the outer radius. It's 6 inch. It's a curved beam. As you see, it's a curved beam. It's a hook for a crane. The inner radius is 2 inch. RO is 6 inch. So 2 inch, 6 inch minus 2 inch is gonna give me 4 inch. This is the center of curvature. This is 2 inch. This is 6 inch. So it tells me it's gonna be 4 inch. So we would like, if we put a weight of 5,000 pounds, if you just put a weight of 5,000 pounds on the hook, which are applied at the middle, we would like to find the stress on this cross section. Find the stress distribution at cross section AA. If I cut it at this cross section, it has a rectangular cross section. So if I draw, I look to the cross section AA from top. So this length is 4 inch. This is Ri. If I look from the top, this is the center, let me label by O. Ri, this is going to be Ro.
Can you explain what's happening?
Okay, I just cut
Oh, okay.
the beam at this cross section. I looked from the top.
Okay.
I will see a rectangular like this. This distance is 4 inch. This thickness is, it's given 0.75. The thickness of the hook. I mean the hook is 0.75. I'm talking about this. This is Ri, this is Ro. Rc would be at the middle. We would like to find the stress applied to this cross section. How the stress is varying over this cross section. Is that obvious? I mean, is any question about this? Everybody can see how did I draw this cross section? Because usually it's where the students might have some question, how did I come up with this cross section? Okay. Now, what I need to do, I need to find any load applied to this cross section. So if I draw the force applied here, and this cross section, one force should go up with the magnitude of 5,000 pounds to avoid the moving of this hook. And this force times the distance. What distance? The distance from centroidal axis, RC, is making bending moment. M would be M with respect to centroidal axis. Force times RC. How can I find RC? It's a RI plus half of 4. Ri plus half of the h, which is 4. Half of the h is 4, 4 divided by 2. So Ri is 2 plus 2 is going to be 4 inch. So 4 times 5,000 is going to be 20,000 pounds inch. So this force is making 20,000 pounds inch moment. The reaction should apply in the opposite direction.
What is? Oh, never mind.
Again, this is where I said moment should be calculated about centroidal axis, not neutral axis. So for that reason, I calculated m with respect to centroidal axis. So now this cross section is about this force. This tensile force is going to make tensile stress. So sigma would be force divided by the area plus sigma due to bending moment. This is due to the axial load, this is due to the bending moment. Because this cross section is under this moment. F divided by 8, 5,000 divided by thickness is 0.75 times 4. It's going to give me this. Now I need to find due to the bending moment. Sigma equals to M. I'm using this. M is 20,000. Rn, what's the value for Rn? I should find the location of the Rn. For rectangular cross section that I have right there, Rn would be ln of h divided by ln of Ri over Ro over Ri. H is 4 divided by ln of Ro is 6, Ri is 2. 6 divided by 2. 4 divided by ln of 3 is 3.64. So this Rn is 3.64. This Rc is 4 inch. So it's before Rc. So 3.64 minus R, I would like to find the stress distribution. So I leave R because it's varying from 2 to 6. R is varying from 2 inch to 6 inch. I didn't specify any point. Divided by A, area, 0.75 times 4 times E. E is defined as Rc minus Rn. E would be Rc, which is 4 minus 3.641 times R. So now the summation of these two is gonna give me the stress over this cross section. If you want to find the stress at inner cross section, at inner radius, you just plug in Ri. At R equals to Ri, which is 2 inch. This is point inner. Is it tensile or compressive due to this? Tensile. It tries to straighten the beam, so this part is going to be the tensile. So for 2 inch, I'm just plugging 20,000 times 3.64 minus 2 inch divided by 7.75 times 4 is going to be 3. 3 times 4 minus 3.64 times 2. It's going to be 15.2 kpsi. Basically, we'll find 15,236 or 15.2 kpsi, just this part, due to the bending. The total sigma would be this divided by this, which is 1.6 kpsi. Sigma would be 1.6, 7 plus 15.2, 16.89, almost 16.9 kpsi. At R equals to RR. Do the same thing for RO. You will find the summation negative 5.63. If you draw this equation, as a function of R, you will end up to this hyperbolic function.
Yeah.
What?
Total
This is the neutral axis. At neutral axis, I mean not neutral axis because we have this part.
You end up with
But if we didn't have
plus.
at the neutral axis, we could get the zero
Yeah,
value.
yeah, yeah.